The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone. My name is Byron Siebold, West Region Sales Manager for Mahr. And I'd like to thank you for joining Mahr's first of many webinars, Basics of Metrology for Optical Manufacturing. And so I also have my colleague online as well, Brent.
Hello, I'm Brent Bergner. I'm the Senior Optical Engineer here at Mahr's facility in Tucson, Arizona.
And so sort of before we jump right into the technical presentation, I'd like to take a moment to introduce Mahr. So this would be very brief. So I do appreciate your patience while I kind of go through these next few slides. So a little bit about us. Some may ask, who is Mahr? Oops, looks like we're jumping ahead in slides. Sorry. What would a webinar be without technical difficulties? So, so some of you may ask, who is Mahr? Some may know Mahr federal or federal, but for those who don't, this will be just a short overview. So Mahr has a long and robust history. Oops, keeps jumping. Around 150 plus years of precision gauging. When the time was fruitful and technology was abundant, Mahr progressed with the implementation of computer-controlled metrology systems. And this was around the late 80s. There's a large gap of information that I'm not going through because it's a long history, as I mentioned, 150 plus years. Which now Mahr provides many companies with advanced metrology systems for a vast range of applications. And with this continued growth, as shown in the current slide, Mahr is nearly 2,000 employees strong. Much of that is comprised of 17 subsidiaries and activities in over 60 countries. So Mahr is a very vast company. As mentioned, it's been around for a long time. And we have a very, very intricate support network throughout the entire globe. In the Americas specifically, sorry, this is, goodness gracious. So in the Americas specifically, Mahr has a very strategic position to support not only the optics industry, but all the other industries, which I'll sort of touch base on in the coming slides. However, just to talk about the Americas a little bit in detail, Providence, Rhode Island is the North American headquarters. Our Tucson, Arizona facility is our center of excellence for our optics division in the Americas. Other facilities to make note of are our Cypress, California facility, comprised of applications, sales, support, and with a fully functional demonstration lab. Lastly, our Erlanger, Kentucky facility is home to our North American service support team. It is also equipped in the same fashion as Cypress, California. But since we're talking about optics and focus on the optics industry for this particular webinar and also our division of the company, which is Mahr-About Us, I'll just touch a little bit on Mahr Tucson. Equally equipped as Erlanger and Cypress, our Mahr-About Us team is comprised of many intelligent and experienced employees from the optics industry with service support, development, expertise in form interferometry, profilometry, and finally, the capability to support rapid prototyping. It sort of brings us gratification to have such a facility for Mahr-About Us in the Americas, especially located in Tucson, Arizona, near the University of Arizona. And we feel very strongly that this is a very key location in the Americas. So Oops. Again, I do apologize. I'm having all kinds of difficulties this morning. So with all these sort of wonderful facilities that we have in the Americas, it's without saying that Mahr has been present and supportive across many different applications for many years. Sort of outside of the optical industry, Mahr has supported many metrology solutions in the automotive, medical, aerospace industries. And but however, today we speak of optics, and this is something which has obtained much invested time and resources to sort of further support the optics industry. So Mars is specializing in providing measurement solutions for applications such as spherical, A-spheres, cylinders, and freeforms, which will be covered in the technical presentation by Brent. Since I'm having so much difficulty with the slides, I'll just go on ahead and start handing it off to Brent. But I want to just take a moment to thank everyone for listening in and joining. It's definitely much appreciated. So now, as I mentioned, moving on to the technical presentation, I'd like to hand it off to my colleague and Mahr-About Us Senior Optical Scientist, Dr. Brent Bergner. So thanks again.
Well, hello, everyone. As Byron mentioned, my name is Brent Bergner, and I'm the Senior Optical Engineer here at our Center of Optical Excellence in Tucson, Arizona. And I'll be speaking to you about some of the basics of, well, it's happening for me too now. Let me try to get back on the slide, the correct slide here. Okay. So hi, my name is Brent Bergner, and I'll be speaking with you on some of the basic concepts for optical metrology as it's applied to the optics industry. As Byron mentioned, Mahr has 150 years of experience in metrology, mostly starting off in the locomotive industry, and then in the automotive industry, we support a lot of industries in medical, aerospace. But one of our key areas of concentration now is in the optics industry, and we're bringing that metrology experience that Mahr has had to this industry. Anyway, I'll be speaking about some of the basic concepts of metrology for optics manufacturing, and in particular, I'd like to address three things. First, the role that spatial frequency content plays in the selection of measurement tools, how that affects the relationship between design, manufacturing, and measurement in the optics industry, and finally, how Mahr is addressing those needs. So I think, as many of you may know, the errors in an optical surface can be thought of as divided into three regimes, depending on the dominant effect that the surface error has on the light propagating through the system. At one end of the spectrum, there are low spatial frequency errors that are often referred to as form errors. They have periods that are much, much larger than the wavelength of light. In fact, for visible systems, you might think of them in terms of fractions of the aperture, so maybe 3 to 5 millimeters or so. These are related to the classical geometric aberrations, such as spherical aberration, astigmatism, coma, etc. And the results, the effect of these form errors is a broadening of the point spread function. So on the other end of the spectrum, there are high spatial frequency errors. These errors are still on the order of several wavelengths, the periods, but they might be on a few hundred microns for the visible. The light is really scattered into more or less a uniform pattern, usually sometimes a Gaussian pattern across the pupil. And we call these errors roughness. These errors usually result in an overall loss in the system or a reduction in the contrast for the system. And then there's this third regime, the mid-spatial frequency regime, sometimes referred to as waviness. These errors result in significant performance degradations in the system, and they're really, really hard to model and predict. The errors are often periodic in nature and can act more like diffraction gratings. So they create peaks in the diffraction of the point spread function that can fall within the pupil and cause significant degradation to the system performance. Unfortunately, as I'll talk about in the next few slides, most of the deterministic generating techniques like MRF and diamond turning, those techniques that are needed to create aspheric and freeform surfaces, leave some kind of error in this mid-spatial frequency regime. So before I go on and talk about some of the sources of these errors and how they are measured, I'd like to briefly talk about a method of visualizing these errors that was presented by Dr. Angela Davies from the University of North Carolina at Charlotte. She presented these last year at the SPIE Photonics and Optics and Photonics Conference in San Diego. So for a, boy, this is very touchy. Anyway, you can think of the surface errors being divided over a circular aperture, being divided up or decomposed into a set of orthogonal polynomials in the azimuthal and radial directions. And one of the ways of doing this is the Zernike polynomials. That's a set of polynomials that are often used to describe errors in optical surfaces. One way of visualizing these is in this triangle, where you plot increasing radial orders from the vertex of the triangle down, and increasing azimuthal surface orders from the center of the base out. Another way of visualizing these is to plot the coefficients of the polynomials in a Cartesian coordinate system, where the horizontal axis is the azimuthal order of that coefficient, and the vertical axis is the radial order of that coefficient. And this way, you can start to divide up and look at the coefficients to understand something about the process and about the surface. In the upper left-hand corner here are those classical Seidel aberrations that I spoke about that cause the low frequency form errors. Along the left-hand side, those are just all rotationally invariant components of the surface error. And then in this area, there looks to be some structure. And what they noticed was that this structure in the bulk of the plot can be related, okay, there we go. That this structure in the bulk of the plot can be related to the process that was used to generate the surface. For example, here's a diamond turn surface, here's a post-polished diamond turn surface, and here's the different signatures for those surfaces. Well, if you can understand these plots and you can get the data in order to make these plots, then you have something that you can use to control the process. But in order to get that data, you need some way to measure it. Before going on and talking about the different ways we have of getting that data, I'd like to talk about a way of looking at the measurement systems. Every instrument that profiles a surface has some range and resolution, both in the lateral and the vertical directions. One way of visualizing that is a Stedman diagram. It was first proposed by Margaret Stedman at the National Physics Lab in the UK. That's their equivalent of the NIST in the US. And if you look at a surface as composed of a series of sine waves with different wavelengths and amplitudes, and you plot out the spatial wavelengths over the, well, this thing has a mind of its own. And if you plot out the spatial wavelengths along the horizontal axis and the amplitudes along the vertical axis, Then the largest amplitude that you can measure, largest amplitude that you can measure is going to be limited by the vertical range of your instrument. The smallest amplitude that you can measure is going to be okay, there we go. The smallest amplitude of deviation that you're going to be able to measure is going to be limited by the vertical resolution of the instrument. The largest amplitude, of course, is going to be limited by the vertical range of the instrument. And likewise, the smallest spatial wavelengths that you're going to be able to measure are going to be limited by the lateral resolution of the instrument. And the largest feature sizes that you're going to be able to measure are limited by the lateral range of the instrument. In addition, many profilers, such as a mechanical stylus profiler, will have a round tip to them. And this tip, the size of the tip, will limit the aspect ratio of the features that you're able to measure. So the smaller the tip, the larger the aspect ratio that you're able to measure. And that's going to put a bound on the types of measurements that that instrument's going to be able to make. And in addition, certain profilers have certain profilers, let's get back to that area. All right. Well, anyway, let's not worry about the graphic, and we'll talk about certain profilers having a geometry to the probe, say the numerical aperture of a scanning white light interferometer, and that's going to limit the slope of the features that you can measure, and that gives you another line over here on this section of the diagram. And finally, the straightness of the slides of a scanning probe system will limit the maximum slope of the error that you can expect to detect, and that's going to give you another limiting area here. And if you plot all of those out, hey, now it's working. There we go. All right, it's going to give you an area, a parameter space that you're going to be able to use that instrument for. Sorry about the technical difficulties we're having here today, but hopefully you'll be able to go back and look at these slides later and get the gist of what we're talking about. So the idea of the Stedman diagram is that different instruments will be able to cover different areas of this parameter space. For example, here are some of the surface profiling instruments in the Mahr-About Us portfolio. We have mechanical profilers, such as the MarSurf LD Aspheric and the MarForm MFU 200. And those can cover a very large area in this parameter space. They can measure very, very small lateral features in very, very large areas. And they can measure a large range of heights. However, they cannot measure quite the resolution of the Fizeau interferometers, such as the Mahr-About Us FI 1100. But the Fizeau interferometers are very limited in the range of lateral features that they can see. Even more limited is, even more limited in the range of feature sizes that it can see is the WM100 scanning white light interferometer. But as you see, it can measure very, very small deviations in the surface height. So now, if you superimpose an area of the, if you superimpose on this an area in the parameter space that represents the surface that you're trying to measure, you can see easily see what instruments will be needed to take those measurements. And as is in this case, very often you'll see that more than one instrument is needed to cover the entire range of spatial frequencies and amplitudes that are of interest for any particular surface. So as you can see, the relationship between optical design, the manufacturing process, and the measurement process is integrally related. The surface forms that you choose in the optical design will determine the generating processes that you'll be able to use for the surface. In turn, the characteristic signatures of the generating process will influence which mathematical models are needed to fully design the system. The generating process will determine the appropriate metrology tools that are needed to fully characterize the surface, like we just talked about. And then that data that you're able to take from those measurement processes will be able to be used to control that generating process. And finally, the types of surfaces that you choose in the design will limit what instruments you're able to use to measure the surface. And then that measurement data will feed back to the tolerance models for the design. So, as you can see, while throw it over the wall may be okay for expedited beer delivery, it's not particularly good for optical component manufacturing. Whoops. Well, with that, I'd like to talk a little bit about Mahr's capabilities for measuring optical surfaces. In its simplest form, Mahr is very, very good at making profilers. We've been making profilers for the automotive industry for 20, 30 years now, and are very good at that. And we've developed a lot of unique technologies. Shown here is the MarSurf LD260. It's a 1D profiler that can take a profile across 260 millimeter length. Each probe for this profiler is embedded with a chip that encodes the calibration data for that probe. And then the force of that probe can be adjusted electronically down to about 0.5 millinewtons. So this reduces the possibility of scratching very sensitive optics like polymer optics or even optics with very soft coatings. To that, we've been able to add some very specialized software, and we use that to create a system that we call the LD260 aspheric. It adds special software for analyzing the aspheric surfaces, and it can even measure mold inserts and micro optics. One of the important parts in being able to mold these surfaces is to be able to fixture them in a sturdy, repeatable, and useful way. Well, darn. There we go. All right. Well, another software add-on for the LD260 allows us to measure and analyze diffractive optical elements. Here in this example, we have measured a diffractive optical element that was diamond turned onto an aspheric surface. With the software, we are able to separate the deviation of the base asphere from the deviation of the diffractive structure, and then we provided that information back to the single point diamond turning machine for correction. And so often when you're measuring optics, you would like to measure a 2D or 3D surface rather than just a 1D profile across that surface. That gives you a lot more information. And of course, we could choose a polar coordinate system or a Cartesian coordinate system. Needed a little bit of humor in the morning. But for most of the Mahr instruments, we found it convenient to use a cylindrical coordinate system, or sometimes we call it a C-axis coordinate system. We've traditionally offered a variety of instruments for measuring shafts and cylinders, and we've adapted that technology for measuring aspheric and freeform surfaces. So in this system, the probe comes into contact or with the surface under test, and the probe is translated along the x-axis while the part is rotated around the c-axis. The probe displacement is then measured in the z-axis, and this information is used to generate a point cloud to represent the surface. We can then fit data to that surface or use that data to calculate surface statistics. We have a full suite of software for analyzing and reporting that data based on our Mahr-Win platform that is extensively used in many other industries. And finally, we've worked with several of the manufacturers of grinding and polishing tools to develop interfaces between the generating process and the measurement process. That way we can create a closed loop manufacturing process for the optics industry. We have another profiling tool that can use an optical probe. This is called the MFU200. And the optical probe uses a superluminescent diode to provide a broadband light source. That light source is coupled into a fiber, and the space between the fiber and the surface under test creates a resonant cavity. When the optical path in that cavity is 1/2 wavelength for any particular wavelength in the spectrum, then there is constructive interference. The light's coupled back into the fiber to a microcinepherometer where it's analyzed. If we plot the contrast of the signal with respect to wavelength, then we get a signal that we call a parallelogram. Now, the probe can be operated in one of two modes. In one mode, we try to keep the peak of that parallelogram in a particular position. So we change the distance of the probe to the surface, we change the distance from the probe to the surface to keep that peak at one position. And then we measure the adjustment of that probe as we scan it across the surface to get the surface data. In another mode, we look at how the peak changes. We keep the probe distance constant, and we look at how the wavelength of the peak as we scan across the surface to get the surface data. So this optical probe that I just talked about can be used to map out a 3D map of the surface. And we can also use a tactile probe to pick up the edge of that lens. So on this particular system, the tactile probe and the optical probe are on the same arm, and we can just switch between the two without recalibrating or moving the optic under test. And then finally, we can use a third mechanical probe to pick up the bottom surface of that lens. So in this way, we can combine these three measurements, the form measurement, the decenter measurement, and the wedge measurement, and get all three of those measurements on one tool without moving the optic. This is often a very difficult task for aspheric lenses. The MFU can also be used to measure freeform surfaces. Here's an example of a freeform mold. In this case, it's very important to be able to align the coordinate system and the measurement tool with the coordinate system of the part. So because we have this multiple probe capability, the MFU can use the tactile probe to pick up fiducials on the part or alignment features on the fixture. And then we use that to align the coordinate system of the part to the coordinate system of the measurement instrument. And we can get a 3D or a topography map of the surface and or the surface air. Mahr also has a full line of phase shifting Fizeau interferometers that have native apertures between 40 and 150 millimeters. We have the option to create apertures up to 300 millimeters with available beam expanders. And then we can integrate those systems into vertical workstations such as this MT300 and the MT100. These are made for shop floor, have very small footprint, and are very stable and are made for shop floor operation. We even offer a vibration insensitive solution that uses a patented 3-camera polarization phase shifting technique. And then, as I mentioned earlier, we have a variety of methods of measuring surface roughness, and one of those is the MarSurf WM100. It's a scanning white light interferometer with a very compact design and small footprint that's, again, acceptable for shop floor operation. And then last but not least, Mahr is known for our benchtop and hand tools, such as calipers, micrometers, and dial indicators. These include a line of gauges that can be integrated with wireless technology and used to transmit data directly to Windows applications for recording and analyzing the data. We've adapted several of these gauges. There we go. We've adapted several of these gauges for specific applications in the optics industry, such as this lens center thickness measurement system that we developed. And we can provide custom engineered solutions to meet special customer requirements. And finally, I'd like to thank our applications and engineering teams, both here in Tucson and at our center in Jena, Germany, for providing most of the data that I use in the examples today. And I'd like to give a special thanks to Dr. Angela Davies from the University of North Carolina at Charlotte for providing those slides on process signatures. So in summary, if you take anything away from this webinar, I hope that you would understand that spatial frequency content has an influence over how an optic is designed, fabricated, and measured, that the design, fabrication, and measurement processes in optics are inherently related, and you have to be able to communicate between each of those processes, and that Mahr has the experiences, resources, and commitment to be your metrology partner in the optics industry. Well, with that, I'd like to hand it back over to Byron, and we'll try to field any questions that you might have.
Thanks so much. Yeah, thanks so much, Brent. Really appreciated. So yeah, as Brent mentioned, if anybody has any questions, please feel free to type them in. We'll give about 3 to 5 minutes, I'm sure, to digest the information and hopefully project some questions. However, I think you guys have my contact information, so feel free to email me separately away from the webinar if you have any additional questions as well that you think of later. And just as a note, I think Brent sort of mentioned in the technical discussion or presentation that we will have this webinar. It's being recorded and will be available for download. We're working with our marketing team as to how that will sort of be done, but most likely it'll be on our website, or we'll email a link to all that attended today for you to be able to download that at your own free will. I think there's quite a bit to take away from this particular webinar. I will sort of lay the groundwork for the future and let everyone know that we will be hosting many other webinars, as I mentioned in my introduction. The next webinar me and Brent are diligently working on and trying to put the title and the abstract together. And basically, we're looking at, and Brent, stop me now before I say too much. But right now we're looking at presenting basically the challenges and opportunities of aspheric metrology. Is sort of the gist of our next webinar in the second quarter of this fiscal year. And then we have some stuff planned for third and fourth quarter as well. So we'll give it a few more minutes. Brent, is there anything that you'd like to add on your side?
No, not right now.
Okay. then I would say that we can. Oh, looks like we have a question. Okay, Brent, I have a question for you. This is from Robert Cartland, and Robert says or asks. Oops.
By the way, thank you.
So he says, show Davy's slide again.
Okay.
And then he says, oops, yep, please.
That may be easier said than done, but
yeah.
we'll try to do it.
Yeah, sorry, Robert. We have, for whatever reason, when we ran our practice run on the webinar, we didn't have so much trouble with the slides. So please be patient. We do appreciate it.
There we go. Oh, well, okay.
So Robert asks, let's see, I have a question about the Fresnel length. It looks like it should have units of length, but also looks unitless.
Oh, okay. So this is on the slide before that.
Oh,
I was
okay.
talking about, so this is Angela Davies' work here, is on the radial axial components of using a lot of Zernike coefficients to represent the surface. Come on. There we go. This is the one out here. And no, it is not unitless because you have the period that's squared and then you're dividing it by the wavelength. So it's got units of whatever the period was. Does that make any sense? Right, and usually you use this Fresnel length to define these different regions. This is from a paper that was given by Dave Akins and Peter Groot. When was that? So back about 10 years ago now. So where they discuss the difference between these spatial frequency ranges. And this is something that's been traditionally talked about, are form errors and roughness and waviness errors, but really there's always been and there still is, there's no sharp definition between each of these regions. And this was an attempt on their part to give some sort of a definition to these regions and a mathematical representation to give a definition of these regions.
So Brent, I'm going to take over the mouse. Okay. And Robert says thanks, by the way, and he'll take a look at the paper as well. So Brent, thanks for making sure to put the notations in there of where this information came from. We have another question, Brent.
Sure.
It's slide on Stedman diagram and measurable area. Just wait a second. Let me see.
Oh.
Could you go back over what causes limit for the minimum slope error? I missed that.
Okay. Yeah, and that was, sorry about that, but I was having some problems with that slide, and so I kind of breezed over that. But the limit for the minimum slope error is given by the flatness of the stage for a scanning system. Let's see if I can get to just that one. And I didn't have a graphic for that either. That might be some of the issue. So there we go. So this minimum slope error, if you've got a stage that is that has some, as you're moving the stage along, it's got some error in the height of the stage. Say it's the flatness of the stage. Then you're not going to be able to measure slopes that are less than, or slope deviations in some case. For some instruments it's slope, for some instruments it's slope deviation that is within the error of that stage.
So I'm
within the slope stage, let's put it that way.
Perfect. Okay, so the person asked the question, that makes sense, and thank you. So thanks, Brent.
So sorry for breezing over that.
Perfect. Okay, so if there are no further questions, maybe we'll just wait just another minute, and then we'll conclude this webinar.
Okay, very good. And while we're waiting for that, I'd like to mention that the Stedman diagram is not always so clear-cut for every instrument. It's a very good way of summarizing the data and looking at how different instruments overlap in their measurement range. But for example, for the Fizeau interferometers, what we're really plotting out is height deviation and slope deviations, and not necessarily the absolute surface shape, because that's what you measure with a Fizeau interferometer. You measure the difference from a reference. So it has to be taken with a grain of salt, but it's a very good way, I think, of looking at how the measurement ranges of the different instruments overlap.
Okay. Well, for those that are still on the webinar, we really appreciate your time that you took from your either work or personal lives to attend this webinar. And we hope that you take a moment to provide any feedback to us, things that might interest you in terms of optical metrology, optical manufacturing, that we could look and investigate into for further webinars to help educate the optical industry, but also any information, just in general, any feedback is greatly appreciated. And you can email me directly at byron.seabolt@mar.com, and I think the majority of you should have my email address. But again, just a great big thank you. And yeah, so we will conclude the webinar and look forward to having you on future webinars. So thanks very much and have a wonderful day.
Thank you.